Hello, and welcome to Mr. Ambrose's video on P-series. To introduce this particular series, I'd like to refer back to some of the series you looked at with the integral test, because essentially those all were P-series. The first of those series was our harmonic series. If you notice there, the general term was in the form of 1 over n. That is our harmonic series, and the harmonic series we know diverges. The next particular problem we looked at had general term of 1 over n squared. This too is an example of a p-series, and here again n squared was in the denominator, and this particular series converged. And then in the video yesterday we looked at two other series. One had general term of 1 over n cubed being in the denominator. There again that series converged. And the last problem from the video yesterday was 1 over the square root of n. Again, square root of n was in the denominator, and that particular series, if you recall, diverged. So all these series are considered p-series because their general form, the form of the general term, is pretty much the same. They're all essentially of the form 1 over n to some power of p. And in order to maintain that form, the power of p in the denominator has to be some number that is greater than 0. Now, p-series you'll perhaps find to be somewhat similar to a geometric series in the fact that they're very easy to determine if they converge or not. There's a particular number for p that is a divider line to where perhaps on one side of that number all p-series will converge, and on the other side of that number it diverges. And if you think about the series that I just went over with you and what those p-values are, you may actually know what that number is or can figure out what the number is. And by no coincidence, that number actually happens to be the p-value for our harmonic series. The p-value there is 1. So in particular, if the p-value to a p-series is greater than 1, we say then that our p-series is going to converge, right? In those examples, when p was 2, p was 3, those p-series converge. And so any other p-value greater than 1, that particular p-series will converge. But if the p-value is less than or equal to 1, but still greater than 0, then those p-series will diverge. Right? Again, our harmonic series we know diverges, and the p-series that had square root of n in the denominator, right, the p-value there was 1/2, and so that p-series diverged. Right? Now, it's somewhat easy to quickly show that p-series works and to actually prove that. So if we consider just any particular p-series, right, we have n equals 1 to infinity, 1 over n to the p power. All the terms of this particular series will be positive, so we could apply our integral test, and in that improper integral that we could set up, the function we could use would be 1 over x to the p power. Right? That particular function will behave exactly like 1 over n to the p power from 1 to infinity. And for this particular function, as x increases, the function will be decreasing and continuous on the interval from 1 to infinity. So we would have to evaluate this particular improper integral. And to do that, right, we would first substitute in a variable for infinity. I'll use t. And then after making that substitution, we have to try to evaluate this definite integral from 1 to t of 1 over x to the p dx. Now to do that, we would have to figure out an antiderivative for 1 over x to the p power. And upon initial inspection, that might seem quite intimidating. But if we get rid of the fraction 1 over x to the p power, we can do that by writing it as x to the negative p power. Remember, p is just a constant. So now we just have a power of x. And to find the antiderivative for this here, we can just do our reverse power rule, which says that we need to add 1 to the power that we have. So we would have x to the negative p plus 1, and then we divide by that new particular power. So that would be negative p plus 1. So that's our antiderivative. And then we can just plug in our limits of integration into that antiderivative. So t is our upper limit of integration, so we'd have negative t to the p plus 1, and that's over still negative p plus 1. And we have to subtract from that the lower limit of integration, 1, so we have 1 to negative p plus 1, all over negative p plus 1. And now that we have this here, we need to still evaluate the limit as t approaches infinity. And to do that, there's a lot going on here, but it's only t that's racing off to infinity. And in this expression, the only place where we see the variable t is right up here. So we could perhaps focus our attention on that expression, because everything else in this entire terms are just remaining constant as t races off to infinity. So we can consider now what is the limit as t approaches infinity of t to the negative p plus 1 going to do. Now, technically, we already know the divider line to when a p-series converges or diverges. So if we take the scenario where p is less than 1, if we consider numbers, if p is a number that's less than 1, then this entire exponent is going to end up being something that's going to be positive. And if we put in infinity in for t here, infinity to a positive number is going to leave us with a positive result. And in this scenario, this means that the improper integral will diverge, and thus our p-series will diverge. Okay, so that's for p-values less than 1. But if p happens to be greater than 1, well, if we consider that scenario, if p is now a number greater than 1, remember that we're going to have to negate that p-value. So whatever that number is, when we negate it and then add it to 1, hopefully you'll agree that we'll end up with a negative overall exponent. And when we plug the infinity in for t, infinity to a negative exponent will always yield an answer of 0. So in this case, our improper integral converges, and so goes our p-series. So this kind of proves when a p-series converges, when it diverges. It's really dependent upon what the p-value is. And to show you quickly an example, we can look at this example here, number 1 perhaps. We want to use our p-series theorem to determine the convergence of this particular series. When you initially inspect it, it may not pop out as being a p-series, but remember, radicals we can rewrite as a power. So that power in the denominator would be to the 4/3 power. So this here is a p-series, and our p-value, right, that's just the power of n in the denominator, and that's 4/3. And since 4/3 is the number greater than 1, this p-series converges. So hopefully you can see from this here, this is a very quick and easy process to determine the convergence of this p-series. So tomorrow when you come in, Master Tam will perhaps do an example or two with you guys with the p-series, and then you'll continue to look at more series and how we can determine whether they converge or diverge. Thank you for watching, and I hope you have a good night. Take care.